Have you ever called a taxi using an app on your phone? Think about what actually happens in that moment. You open the app, type in your destination, and within seconds, a driver is on their way to you. You did not call the driver directly. You did not know the driver's phone number. You did not even know which driver would pick you up. And yet, somehow, the whole thing worked perfectly. Now here is the fascinating question. How did your phone know which driver to send your request to? How did the system juggle thousands of other passengers doing the same thing at the exact same time? The answer lies in a powerful idea in software design called the broker architecture pattern. In this video, we are going to break down exactly what the broker architecture pattern is, how it works, why it matters, and how it powers some of the biggest apps and platforms you use every single day, including Uber, WhatsApp, and even financial stock exchanges. Whether you are a student just starting out, a working professional in technology, or simply a curious person who wants to understand how modern software is built, this video is for you. So let us get started. Before we explain what the broker pattern is, let us understand the problem it was designed to solve. Imagine you are building a large software application. Your application has many different parts. Maybe one part handles payments, another handles notifications, another manages user accounts, and yet another handles shipping. Each of these parts needs to talk to the others. In the early days of software, developers would connect these parts directly to each other. The payment system would reach out directly to the notification system. The notification system would reach out directly to the shipping system, and so on. At first, this seems perfectly fine, but as the system grows, the connections start to multiply very quickly. Imagine 20 different parts all connecting to each other. The number of direct connections becomes enormous. And every time you want to add a new part, you have to update every other part that needs to talk to it. This is what software engineers call tight coupling. Every component is tightly tied to every other component. If one part breaks, it can bring down the whole system. If you want to change one part, you might accidentally break 5 other parts. The system becomes fragile, difficult to manage, and very hard to grow. The broker architecture pattern was designed specifically to solve this problem. It introduces a smarter, more organized way for all the parts of a system to communicate with each other without anyone needing to know who else is on the other side. The broker architecture pattern is a software design approach where a central component called the broker sits in the middle of all communication between different parts of a system. Instead of every part talking directly to every other part, all communication goes through this central broker. Think of the broker as a post office. When you want to send a letter, you do not personally deliver it to the recipient's house. You bring it to the post office, and the post office takes care of routing it to the right destination. The sender does not need to know exactly where the recipient lives. The post office handles all of that. In software, the broker works in exactly the same way. A part of the system, which we call a client, sends a request to the broker. The broker figures out which service or component can handle that request, forwards it appropriately, and then brings the response back to the client. The different parts of the system are called servers in this context, not because they are physical machines, but because they provide services or capabilities that others can use. So to summarize the key players. First, you have the client. This is the part of the system that needs something done. It sends a request. Second, you have the broker. This is the central coordinator. It receives the request, finds the right service, passes the request along, and returns the answer. Third, you have the server or service. This is the part of the system that actually does the work and returns the result. The magic here is that the client and the server never need to know about each other directly. All they know about is the broker. This separation is what software architects call loose coupling, and it makes systems far more flexible, scalable, and maintainable. Let us make this even more concrete with a real-world analogy that most people are familiar with, a stock exchange. Imagine you want to buy shares in a company. You do not call up a random shareholder and negotiate with them directly. Instead, you place an order through a stockbroker or a trading platform. The exchange itself acts as the central middleman. It matches buyers with sellers based on their needs, price, quantity, timing, all without the buyer and the seller ever needing to know who the other person is. The stock exchange is, in essence, a broker. It manages all communication between those who want to buy and those who want to sell. It enforces the rules. It keeps records. It ensures orders are matched correctly and fairly. Now replace buyer with client software. Replace seller with service or server, and replace stock exchange with software broker, and you have the broker architecture pattern in a nutshell. This is exactly why companies like Goldman Sachs use message broker systems like Apache Kafka to process real-time market data. Their high-volume trading platforms need to handle enormous amounts of information every second, matching requests and responses at incredible speed, and the broker pattern makes all of that possible. Now that we understand the concept, let us walk through exactly how the broker architecture pattern works, step by step. Step 1. A service registers with the broker. When a new service or capability is available in the system, it registers itself with the broker. It essentially says, "Hello, broker. I am here, and this is what I can do." The broker keeps a directory of all available services. Think of this like a business listing in a directory. Any business that wants customers to find them adds their name, location, and what they offer. Step 2. A client sends a request to the broker. When a client wants something done, it sends a message to the broker. The message is written in a standard format that the broker understands. The client says, "I need this task completed," but it does not say who should do it. Step 3. The broker finds the right service. The broker looks through its directory of registered services and finds the one best suited to handle the request. This is the routing step. The broker knows where everyone is and what everyone can do. Step 4. The broker forwards the request. The broker takes the client's request and sends it to the appropriate service. The service does not need to know where the original request came from. It just receives the task and gets to work. Step 5. The service completes the task and returns the result. Once the service has done its work, it sends the result back to the broker. Step 6. The broker delivers the result to the client. Finally, the broker takes the result and passes it back to the original client. From the client's perspective, it sent a request and received an answer. Simple and clean. This entire flow happens automatically and often in just milliseconds, even when millions of requests are happening at the same time. Let us now look at a real-world example that demonstrates the broker architecture pattern in action, and one that most of us have experienced firsthand. When you open the Uber app and request a ride, an enormous number of things need to happen almost simultaneously. Your location needs to be captured. Nearby available drivers need to be found. A driver needs to be matched to your request. The fare needs to be calculated. An estimated arrival time needs to be computed. A notification needs to be sent to the driver. And a confirmation needs to come back to you. Now here is the key point. None of these steps can happen one at a time while you wait. And none of these individual services, the driver matching service, the fare calculation service, the notification service, should be directly talking to each other. That would create exactly the kind of fragile, tangled mess we described earlier. Instead, Uber uses a message broker, specifically Apache Kafka, to coordinate all of this. When you request a ride, the app publishes a message to the broker. The broker then distributes that message to the relevant services. Each service picks up the part of the task it is responsible for and processes it independently. In fact, Uber processes over 100 million ride requests every single day through this kind of broker system, all with very low processing delays. That scale would simply be impossible without the broker architecture pattern. The broker is what allows Uber to add new features like a new type of service or a new payment option without rebuilding the whole system from scratch. New services simply register with the broker, and they are instantly available. Here's another example that is even closer to everyday life: messaging applications like WhatsApp, Slack, or Microsoft Teams. When you send a message to a friend on WhatsApp, your message does not travel directly from your phone to your friend's phone. Instead, it goes to a central server which acts as a broker. The broker stores the message temporarily and then delivers it to your friend's device when they are available to receive it. If your friend's phone is offline, the broker holds the message and delivers it as soon as they come back online. This is a form of the broker architecture pattern. The broker is managing the communication between sender and receiver without them needing a direct real-time connection. Airbnb, for instance, uses a message broker called RabbitMQ to power the communication between hosts and guests on its platform. Given the enormous volume of messages exchanged on Airbnb every day, the broker ensures that every message is reliably delivered, even during peak traffic periods. Now let us take a slightly deeper look at the components that make up a broker system, so you have a complete picture. The first component is the broker itself. The broker is the heart of the whole system. It is responsible for receiving messages, routing them to the right destination, and returning responses. The broker maintains a registry, a directory of all available services. It must be designed to be extremely reliable and fast because everything depends on it. Think of the broker as an air traffic controller at a busy airport. Every plane that takes off or lands needs to communicate with the controller. The controller does not fly the planes, but nothing works without them. The second component is the client proxy. In many broker systems, there is a small helper component on the client side called a client proxy or client stub. This proxy is what the client actually talks to. It handles the technical details of packaging the request into the right format and sending it to the broker. From the client's point of view, making a request feels simple. The complexity is hidden behind the proxy. The third component is the server proxy. Similarly, on the service side, there is often a server proxy. This is the counterpart that receives the forwarded request from the broker, unpacks it, and passes it to the actual service. It then packages the result and sends it back. The fourth component is the bridge. In some larger systems, you might have multiple brokers in different physical locations or networks. A bridge connects these brokers together, allowing them to share information and route messages across boundaries. Together, these components create a robust, flexible pipeline for communication across a distributed system. Let us talk about the key advantages of using the broker architecture pattern, because understanding these benefits is what will help you recognize when and why to use it. The first major benefit is loose coupling. Because components communicate through the broker rather than directly with each other, they are independent. You can change, update, or even replace one component without affecting the others. This makes the system much easier to maintain and evolve over time. The second benefit is scalability. Because services are decoupled, you can add more services or more instances of the same service without disrupting anything. If your notification service is getting overwhelmed, you can simply add another instance of it, and the broker will start distributing work to both. This is exactly how companies like Uber handle surges in demand. The third benefit is flexibility. New services can be added to the system simply by registering them with the broker. The rest of the system does not need to change. This makes it easy to grow and evolve the system over time. The fourth benefit is fault tolerance. If one service goes down, the broker can route requests to other available services. Some brokers can also hold messages in a queue until the recipient service comes back online, ensuring that no data is lost. The fifth benefit is centralized control. Because all communication flows through the broker, it is much easier to monitor what is happening in the system, enforce security policies, log activity, and manage traffic. Of course, no design pattern is perfect for every situation. The broker architecture pattern comes with its own set of challenges that you should be aware of. The first challenge is the single point of failure risk. Because everything depends on the broker, if the broker itself goes down, the entire system stops working. This is why production systems spend considerable effort making the broker highly available, often running multiple copies of it across different machines so that if one fails, another takes over. The second challenge is performance. Adding a broker in the middle of every communication does introduce some overhead. Every message has to travel an extra step. For systems where speed is absolutely critical and the difference of a few milliseconds matters greatly, this added step requires careful design. The third challenge is complexity in the broker itself. Because the broker is so central and so important, it must be exceptionally well-written and thoroughly tested. A poorly designed broker can become a bottleneck that slows the whole system down. The fourth challenge is security. Since all communication flows through the broker, it becomes a very attractive target for attackers. Securing the broker with proper authentication and encryption is essential. Understanding these trade-offs is what separates good software design from great software design. By now, you might be wondering just how widespread this pattern really is. The answer is it is everywhere. Apache Kafka, one of the most popular broker platforms in the world, is used by companies including Netflix, Twitter, Spotify, Pinterest, LinkedIn, Airbnb, and Uber to manage real-time data streams at massive scale. RabbitMQ, another widely used message broker, powers asynchronous communication in countless applications, from healthcare systems to financial platforms to e-commerce platforms. Microsoft Azure Service Bus, Amazon Simple Queue Service, and Google Cloud Pub/Sub are all cloud-based broker services offered by the 3 largest technology companies in the world, which tells you how fundamental this pattern has become to modern software infrastructure. Even your smart home devices use a form of this pattern. When you ask a smart speaker to turn off the lights, a message broker is coordinating the communication between the voice assistant and the smart light system. Air traffic control systems, online banking systems, healthcare record systems, the broker architecture pattern is woven into the fabric of modern technology. Before we wrap up, it is worth briefly comparing the broker pattern to a couple of related ideas you might come across. The first is the mediator pattern. The broker pattern and the mediator pattern are similar in that both use a central component to manage communication. However, the mediator pattern is typically used within a single application to coordinate the behavior of objects, while the broker pattern is used across distributed systems, multiple applications, services, or machines communicating over a network. The second is the publish and subscribe pattern. This pattern, often called pub/sub, is closely related to the broker pattern and sometimes runs on top of it. In a publish-subscribe system, some components publish events or messages without knowing who will receive them, and other components subscribe to receive only the messages they care about. The broker in this scenario acts as the central hub that receives published messages and distributes them to the right subscribers. Apache Kafka and RabbitMQ both support this style of communication. Knowing the difference between these patterns helps you choose the right tool for the right problem. Let us quickly recap what we have covered today. The broker architecture pattern solves the problem of tightly connected, hard-to-manage software systems by introducing a central broker that handles all communication between components. The main players are the client, which makes requests, the broker, which routes those requests, and the service or server, which fulfills those requests. The pattern offers major benefits including loose coupling, scalability, flexibility, fault tolerance, and centralized control. Its trade-offs include the risk of a single point of failure, added communication overhead, and the need to design and secure the broker carefully. And it is used in some of the world's most important and widely used technology systems, from ride-hailing apps to messaging platforms to financial trading systems. Software architecture can sometimes feel like an abstract topic full of terms and diagrams that seem disconnected from the real world. But as we have seen today, the broker architecture pattern is not abstract at all. It is the invisible backbone behind the apps you use every single day. The next time you request a ride, send a message to a friend, or watch a recommendation pop up on a streaming service, take a moment to appreciate the elegant design that makes it all possible. If you found this video helpful, please give it a like and share it with someone who might benefit from it. And if you have questions or want to dive deeper into software architecture patterns, let us know in the comments below. Thank you for watching.